Okay, so we left off with question 524b, and we said we're going to draw all the possible stereoisomers. Well, in this compound, we have a total of 2 stereocenters, so the maximum number of stereoisomers that we could have would be 2 to the power of 2, which is 4. So that means we're going to either have 4 or less. I'm going to erase some of the spinach that I put up here before, since we have our meso compound there. All right, so let's start with some wedges and dashes. So we'll draw our parent chain, which has 4 carbons. We could do that a little better. There we go. So we'll draw a wedge and then a dash at that chiral center. And then what we'll do is we'll flip it. So we'll flip the wedge to a dash and the dash to a wedge. So let me just paste that over here. All right. So we'll flip our wedge. We'll make that a dash. And we'll change this dash. We'll just shade it in. That'll work. There we go. So there we go. So those 2 compounds would be enantiomers, right? Because they're non-superimposable mirror images. Or you could say every wedge is flipped to a dash, every dash is flipped to a wedge. And then, of course, we could also have something that looks like this, where we have 2 wedges, let's say. And if I pencil those in, so this one, hopefully you can see that this is a meso compound, right? There's a plane of symmetry through here. And so since this is a meso compound, I don't have to draw the compound where there's 2 wedges because it would be the identical compound. All right, so in this case, we have 3 stereoisomers, just like the first one. Give me a thumbs up if you're with me on that one, or does anybody have a question about that one? You guys follow me on that question with the meso compound? Cool, great. Again, like I said, students are usually very, very good at recognizing meso compounds. One of those topics that will even come up in organic chemistry too, out of nowhere, and students usually really remember it very, very well. So I know that not all of you, but many of you have studied biology at a high level at the college level, and so you would have seen probably the structure of glucose written in what's called a Fisher projection, and we talked about these briefly when we looked at molecular representations. And so if I just put the structure of glucose, again, you might recognize this from a biology textbook. So it looks something like this, and then you have something down here, and you get a total of 1, 2, 3, 4 chiral centers. So we have a hydroxyl here, here, and here, and then we have a proton here, here. This is a hydroxyl, and this is a proton. So this is called D-glucose. And the reason it's called, the reason for the D, it's got something to do with this stereocenter here. That's something that we'll cover at the end of organic chemistry too. So don't worry about it for today. But again, I'm sure a lot of you have seen Fisher projections, kicking around your classes. And so if you go back to chapter 2, when we talked about molecular representations, we did talk about how when you have a Fisher projection, the vertical lines are on wedges. They're going back into the page, whereas the horizontal lines are coming out towards you. As one of my students said one time, it's like they're coming out to hug you. Anyhow, I never forgot that. I thought it was so funny. And so what does that mean? What that means is since the hydrogen is coming out, it's not going in back, then what we're going to do is we're going to prioritize the groups. Let's say we have the hydroxyl is 1, the ethyl is 2, the methyl is 3, the proton is 4. Well, again, since the proton is horizontal, that means it's coming out towards us. So whatever we read, R or S, we're going to reverse it. So if with this compound, if we were to go 1, 2, 3, like that, it's going clockwise, which would be an R compound, but we reverse it. And so it turns out that this stereocenter is an S stereocenter. So again, usually the hydrogen is going to be in the horizontal position. It is most of the time, not always, but most of the time it is. And so why were Fisher projections developed? Well, I think I told you this before. They were developed by a guy named Emil Fischer when he was categorizing and characterizing all these different sugars. And he said, well, they have so many stereocenters, and he needed a simple way to keep track of all the stereocenters. So you can see here that we have 2 chiral centers in this compound. Here we have 1, 2, 3 chirality centers, 1, 2, 3, 4 chiral centers. And so with sugars, we have lots of chiral centers. And so we have to find ways to keep track of them. So another utility of Fisher projections is it allows you to quickly assess relationships that are stereoisomeric. So you can see with the first two compounds that both stereocenters are flipped, right? They're both reversed. So these two compounds must be enantiomers. Here, one of them is flipped. So this one is flipped, but the other one is identical. And so those must be diastereomers. Okay, so again, Fisher projection is very useful for that kind of thing. So what we want to do now is we want to take these two compounds. The first one is an amino acid, and we want to designate the chirality at each chiral center here. So we have a chiral center here, and this one I think is, I don't like to use the word straightforward in chemistry class, but I think it's not that bad. Okay, nitrogen is going to be number 1. This carbon is attached to oxygen, oxygen, oxygen. This carbon is attached to oxygen, hydrogen, hydrogen. So we can see the tiebreaker is here. So that means that this is going to be number 2. This will be 3. Hydrogen is, of course, number 4. So we're going to take our pen and we're going to go 1, 2, 3, and we're going counterclockwise, which would be S. But remember, we reverse it since the hydrogen is coming out towards us. And so this is an R stereocenter. All right, for the next one, again, the hydrogen is horizontal. So whatever we read, we're going to flip it. So here we have our oxygen is going to be number 1. Our hydrogen is going to be number 4. This carbon is attached to hydrogen, 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 lowly methyl group. This one is attached to oxygen, oxygen, hydrogen. So here's our tiebreaker. So this is 2. This is 3. So we're going to go from 1 to 2 to 3. So that is going clockwise, which would be R, but we're going to reverse it. And so this would be an S compound like that. So that is how you read stereochemical designation, or you apply the Kahn-Ingold pre-log rules when you have a Fisher projection. So remember, if your hydrogen, which is the lowest possible group you can have, it's got an atomic number of 1. If that is horizontal, you always flip the designation, R to S or S to R. Okay, so conformationally mobile compounds. This is something that, you know, I don't spend a lot of time on this, but it is kind of interesting food for thought. If you think about a butane molecule, so if you just take plain old butane, 1, 2, 3, 4 carbons, okay? You guys are all perfectly aware that you can rotate around this bond. And we've also looked at Newman projections, right? We looked down this carbon-carbon bond and we drew Newman projections just like this one here. And you can see that we have a gauche, right? We have a gauche interaction here, and then we have a gauche interaction here. But if you look at these two conformations, are they identical? No, technically they're mirror images of each other, aren't they? So these two conformations are actually chiral. Okay? It's something that I wouldn't have thought about it until somebody showed me. But these two conformations are mirror images. They're stereoisomers, right? The arrangement of the methyl groups in space is different. However, if you look at butane, there's no centers in the molecule, and we don't consider butane to be a chiral compound whatsoever. It's not, okay? Because why? Because we know that this rotation occurs so readily that these things are in equilibrium with each other, and so they're going to cancel each other out, okay? So they're interchangeable so quickly that butane is not a chiral compound, okay? So again, the conclusion is butane is not a chiral compound, but you should know that these two conformations here, yes, they are technically chiral, and they are enantiomers of one another, but the compound overall is rotating so quickly that you can't distinguish between the two. So butane is not a chiral compound at all. So again, what I said about, you know, having to have a stereocenter to be a chiral compound, that still stands. Okay, we're not going to break that rule ever. Now, if you look at cyclohexane, that's kind of cool too. So here we have cis 1,2-dimethyl cyclohexane, and then we have a chair flip. So this is just another conformation. And if you look at the two, you can clearly see that these two are enantiomers, right? They're mirror images of each other. Okay, so it says here that these two conformations are chiral as well, and they're mirror images. However, we know that this ring flip occurs in, they both have an equal stability. They both have one axial methyl, and they both have one equatorial. So there's no difference in the energy between these two compounds. And so they're both going to be equally abundant. So they're going to interconvert. And so the compound is achiral overall. And if you draw it in this fashion here in a Haworth projection, you can see that this is actually a meso compound. Is that weird or what? Right? If you just look at this compound, you can't tell that that's a meso compound by looking at the chair, can you? Right? But if you look at the planar way of drawing it like this, then you can tell it's a meso compound. So it's good to know how to draw chairs and then compounds in a plane as well. So again, the take message is the compound is not chiral because it's a meso compound. But if you look at these two chairs, yeah, technically they would be enantiomers, but again, they interconvert so rapidly that we can't distinguish between the two of them. Section 5.9, chirality without chirality centers. We're going to skip that, as well as the section on resolving enantiomers, so separating enantiomers, which have the same physical properties. I will leave that as an FYI, okay? I would recommend reading through it, which I think both of these sections are really short, but I would just kind of thumb through it and check it out very quickly. Sorry about that, everybody. So I would go through those kind of quickly. And then the last section is actually very, very important. So if you've fallen asleep, wake up now, because the designation of E and Z is super duper important. Okay, everybody has to know how to designate E and Z in organic chemistry. And it's just a way of distinguishing between diastereomers that you can't use cis and trans for. Okay, so if we take a look at these two molecules here, you can see that they have the same number of carbons in their parent chain. 1, 2, 3, 4, 1, 2, 3, 4, right? On the first carbon, you have a hydrogen and an amine. On the second carbon, you have a fluorine, right? So they have the same connectivity, but are these two compounds identical? No, you can clearly see that they aren't. You see the fluorine and the hydrogen are on opposite sides, and they're on the same side here. So you might wonder, why can't we use cis and trans to designate these compounds or to differentiate between these two compounds? If you don't remember, I'll tell you again. Cis and trans with a double bond, you can only use it when you've got two groups on the two carbons that are identical, like X and X. You can't say that X and Y, you don't say that those are trans to each other, okay? Technically, we would say that they're E. So to use cis and trans, you're dealing with groups that are identical. And in this compound, you have an ethyl, a fluorine, a hydrogen, and an amino group. So none of them are the same. So you can't use cis and trans. In this case, you have to use what's called E and Z. So E, you'll have to forgive me, my German isn't so good, but E stands for entgegen, which is opposite, and Z stands for zusammen. I don't even know how to spell zusammen. Maybe like that. Anyhow, which means together. Okay, so we have entgegen, and sometimes my students told me this years ago, is they called it opposite. Okay, so instead of opposite, so opposite, so E for opposite, and that's what entgegen means, and Z for together. Anyhow, I never forgot that. I thought it was kind of funny. Maybe they didn't come up with it, but I never forgot it. Anyhow, so here's how you prioritize E and Z. You guys remember the Kahn-Ingold Prelog rules, CIP, where the higher atomic number takes higher priority? That's how we do it with this, okay? We base it off atomic number. So if we look at the carbon in the double bond on the left, look at the carbon on the left of the double bond, okay? You have a carbon attached here and you have a fluorine. What's a higher atomic number, carbon or fluorine? Fluorine is a higher atomic number. Then you go to the carbon on the right, I'll put it in green. You have a hydrogen and a nitrogen. What takes precedence? A nitrogen. There you go. So now the two highest groups are on the same side. So we highest groups on same side. So highest groups on same side. Therefore, the compound is a Z compound. It's a Zusammen compound, okay? If they were on opposite sides, like they are here, the fluorine and the nitrogen, then it would be an E compound. Now, if you're wondering, what if they're all carbons? Then what do I do? Well, if they're carbons, then you would use the same way or the same thing that you did with the Kahn-Ingold Prelog rules, is you keep going until you find a point of difference. So the exact same rules apply as did for the Kahn-Ingold Prelog rules. There's nothing really new there. So now that we have that, let's see if we can designate the following alkenes as E or Z. So I'm going to highlight this carbon in red, and I'll highlight this carbon in blue. Okay, so on the carbon in red, there's two groups, right? There's this propyl group, and then there's this butyl group. Okay, so which one is going to take precedence? Okay, because this is a carbon, and this is a carbon. Well, the carbon on the top, if I go away from the carbon in red, just like the Kahn-Ingold Prelog rules did, It's attached to a carbon, carbon, and a hydrogen, whereas this one is attached to a carbon, hydrogen, and a hydrogen. So this is the tiebreaker. Therefore, this group is going to take precedence over the butyl group. Then if I go to the blue one, well, I have a hydrogen, and then I have an isobutyl group. Well, obviously an isobutyl group that's got a carbon on it is going to take precedence over the hydrogen. So could anybody tell me, based off of those two groups, which take the highest priority, would this be an E compound or a Z compound? And it's not a trick. Is this an E compound or a Z compound? So the two groups are they on the same side of the double bond or opposite sides? Right, they're on opposite sides of the double bond, right? One of the groups, so look, one of the groups, so if we highlight the double bond, like this, right? One of the groups is going up like this, the other one is going down like this. So this is an E compound, right? Okay, let's try the next one. We'll see if we can get some redemption on this one. I'll highlight this carbon in red. We'll highlight this carbon in blue. So if I look at the carbon in red, what's going to take precedence? I've got a chlorine and a carbon. Who takes precedence? Which one has a higher atomic number? Thank you. Good. It's the chlorine. And then on the carbon in blue, I've got a hydrogen and I've got a carbon from a methyl group. Which one takes precedence? Well, it's the carbon from the methyl group. So now, is this an E compound or a Z compound? Anybody? Exactly, exactly. So this would be a Z compound. And there you go. You've covered all of chapter 5. Hot dog, we have a wiener. Come on, computer. There we go. All right.